valued functions that may have different numbers of inputs to outputs. Luke asked a question at the end of last class about integrals, and we talked a little bit about why are we doing integrals after vector valued functions, because with integrals, you may want to do change of variables in your integral. If you're integrating over Rn, you have n dimensions, and you want to introduce a coordinate change, well, that's a function from Rn to Rn. And we need to understand how these vector-valued transformations work. If you're trying to approximate a PDE numerically, what do? You say, I can't do this in all of space. I'm going to lay down a grid, and I may have lots of different grid points. And now to each one of these points, I might associate information about temperature, wind velocity, all of these things, and now all of a sudden I might have a million inputs here, right? Because when I discretize space, there could easily be a million points that I'm discretizing, and a million or 5 million or whatever outputs in my function. So, all the time we want to do functions that not only take in vectors but also spit out vectors, and maybe very, very large vectors. And that, the hand calculations that we do to make sure we understand how the theory works will be in 2D, 3D, easy, but we want the theory in place to help us do really big problems where either we can't solve things analytically or they're just massive. Okay, so chapter 6.1, I'm really not going to go into today, but it's just about linear transformations. It's basically a little review of linear algebra. If you're rusty on linear algebra, then please read chapter 6.1. Well, I'm not going to need a ton of obscure results from linear algebra, but make sure you're familiar with the basics of matrices. So let's jump into 6.2 then. Continuity and differentiability. Okay, and as when we started our last section, our last chapter, the beginning we'll build up some basic definitions that will be very, very familiar, but then we'll let us start to build on to some more sophisticated results that we might use in a setting like this where we have a million unknowns that we're trying to solve for. Okay, so we have a function. So it's a vector-valued function, so it takes in a vector and it spits out another vector. And they may have the same size or they may not have the same size. Okay, so we can define a lot of the things that we're interested in essentially the identical way as we have before. Now we just have extra components to worry about. We've already had the experience of moving from 1D to extra components in the inputs. So to move from 1D to extra components in the outputs is going to look the same. Okay, so continuity. Let's let x naught be in the domain of our function, if we're going to talk about continuity. Let it be a limit point, okay, of our domain so that we can actually approach it. Okay, then as usual, we say that f is continuous. At the point x naught if all right, and now it's our usual definition of continuity, epsilon deltas, and the limit is the function value. So if for all epsilon greater than 0, we can find some delta greater than 0, such that whenever x is a point in our domain and x is within a distance delta of x naught, then, well, this is the point where we would usually say f of x minus f of x naught is less than epsilon in magnitude. F is a vector now, right? So we're not just doing straight subtracting and then have a number. But we do exactly what we did for the inputs here, right? This is a vector. All we're doing is taking the length of the vector. That's all we're going to do here. We're going to say the length of f of x minus f of x naught can be made less than epsilon. Okay, so let's run a quick example. Again, the examples are not different really from one dimension, but there becomes more and more things to keep track of. So let's suppose that we have a function that goes from R2 to R3. And I'm going to define it this way. Okay, f of x all right, x plus y, xy, and 2x minus y. And let's show that this is continuous everywhere. So let's show f is continuous for all x naught, y naught in R2. Okay, so what do? We pick an epsilon. Usual way of starting these arguments. Pick an epsilon. We're going to look at points in our domain. Well, our domain is R2, so just any x, such that this is true, and now we got to work out what delta should be. Okay, so let's consider x minus x naught less than delta, and we don't know yet what delta is going to be. And we have to write down f of x minus f of x naught and then take its length. So let's write this down first of all. This is going to be a vector now. Okay, so what am I going to have? I'm going to have x plus y minus x naught minus y naught, xy minus x naught y naught, and 2x minus y minus 2x naught plus y naught. We are going to have to take the length of this, certainly. We should, I guess, expect that we're going to want things like x minus x naughts and y minus y naughts to pop up. So we should probably write it in that form. All right, so I'm just going to try to join these together. See what I have here. I have an x times y minus y naught. Okay, then I have to add plus x y naught back in. Plus y naught x minus x naught. And 2x minus x naught minus y naught. Okay, and then we need to take the length of this. So we'll take the length of it. We'll do the other usual thing we do and say that we like length squared better than length. That's probably easier to work with. Saves us writing a giant square root sign on every line. Okay, and then we just start simplifying. So what do we have? We have x minus x naught plus y minus y naught, all squared, plus. write x as x naught plus x minus x naught, y minus y naught plus y naught, x minus x naught all squared, plus all of this squared. And then we know that everywhere we see an x minus x naught or a y minus y naught, that's bounded by the length of the vector x minus x naught, okay, which in turn is bounded by delta, whatever delta is. Okay, so then we can say, well, let's do that. We have that less than delta plus delta squared plus absolute value of x naught plus delta times delta plus absolute value of y naught times delta all squared plus 2 delta plus delta all squared. All right, so what have I done here? Everywhere I see an x minus x naught, I just say it's less than delta in magnitude. Everywhere I see an x naught or a y naught, I bound it by its absolute value. All right, and then we can start to try to simplify a little bit. Okay, so what do we get here? We get 4 delta squared plus x naught plus y naught plus delta squared times delta squared plus 9 delta squared. Okay, so I've got a nice delta squared running through here, which will be kind of easy to solve for. With this, x naught is a constant, is some constant, y naught is some constant. This delta came from in this x minus x naught. But we could say, let's let delta be less than 1, right? As long as we've got our delta sitting out here, we can make whatever assumptions we want about delta in here. So if we let delta be less than 1, we're going to get that all of this is bounded by, well, let's see, 4 plus 9, 13 plus x naught plus y naught plus 1 squared times delta squared. Right, so it's our usual simplification approach. There's just more terms floating around than usual. And then what's our goal? Our goal is to make the length of f of x minus f of x naught less than epsilon. So when we've simplified as much as we could, I say, well, I want this squared to be less than epsilon squared. And then I say, well, indeed, I can do that as long as delta is less than epsilon over the square root of all this stuff. Right, and then we're done at this point, right? We say as long as this is true and this is true, we can certainly force the length of f of x minus f of x naught to be less than epsilon. So we say, okay, great, let's take delta to be less than the min of these things. Minimum of 1 and all of this. Plus 1. Plus x naught plus y naught plus 1 squared. And that recovers the definition. Yes?
Can you split this vector in a matrix and a vector, which the vector will be Rx minus x0?
Sorry, what was the first part of your question?
So split this vector.
This vector?
Yeah, the one that you brought now.
This guy here?
Yep.
Yep.
In a matrix times a vector. And then the vector will be x minus x0.
Right, you could write this in that form, sure.
And then use cosine bars.
Sure, yeah. In this particular case, x minus x naught appears kind of linearly here. Yeah. Yeah, I don't claim this is the only way to do it or that's the easiest way to do it. I mean, we know from real valued functions that things that are continuous, right, things that are built out of these polynomials rather are continuous, and all of those results are going to extend naturally to this. So you're not in practice going to do this exercise on this particular example. But it's good to see where this definition comes from and how to use it, because on some examples, some problems, you do need to go back to the definitions. Other questions on this? So that's continuity. Then we can also extend the definition of differentiability pretty easily. Okay, so differentiability, I mean, we kind of hinted at it a little bit last week because we did the chain rule and our inner function was this vector valued function. And I kind of said already what I mean by differentiability. I just mean that our function, you know, it's a component, each component of this is a function, and we want each of these components to be differentiable. So we should be able to use that to write down a definition of differentiability for objects like this. Okay, so for our function f from Rn to Rm to be differentiable, we want all components to be differentiable. Okay, so we know what that means. We know that this means that the limit as x goes to x naught. All right, let's write this down for the ith component. So fi of x is now a scalar valued function for each of these i's from 1 to m. So we want this minus the function at x naught minus. All right, we have to sum through all the partial derivatives. Okay, so we're going to sum through all of the partial derivatives up to n. Okay, right, so f is a function of n variables, so we have n different partial derivatives to sum over. So we'll take the partial with respect to xj at our point x naught times xj minus x naught j, and divide by the length of x minus x naught, and we want this to be equal to 0. Again, for all these different values of I. Okay, so this is an object we have for I equals 1, I equals 2, I equals m. I could make a big vector and put these as its components, right? And then I'm taking the limit of a vector, and I want that limit to be the 0 vector. Okay, so we could take all of these. Okay, take the limit of an m vector. And these are the components. Okay, we need some more compact notation to do this. So for each I, what do we have here? For each I, we have to take the partial derivatives with respect to all the different components. We're going to store those in a vector, and that's going to be called the gradient vector, the gradient of fi. Okay, and then we're going to say we need to do that for I equals 1 through m. So we have all of these different gradient vectors. We're going to store them together, and we're going to end up with a matrix with all of this derivative, partial derivative information. And this is going to be called our Jacobian matrix. So let's store all these partial derivatives in a matrix, which we'll call the Jacobian matrix. Okay, so this is going to be a matrix, m by n matrix, which we're going to write as the Jacobian of f. We'll use the gradient symbol, let's say at x naught, right? Because we're evaluating all of these partial derivatives at x naught. Okay, and then we're going to have simply that the ijth component of it so for each component of this matrix, ij, okay, again, I equals 1 to m. We run through all the components of f. J equals 1 to n. We run through all our variables. And this is simply going to be precisely this partial derivative. So partial of fi with respect to xj. Now, if we go to do the ith component of this object, we want to write the ith component somehow in terms of that matrix. Okay, so let's have a look at this. If we look at this Jacobian times x minus x naught, all right, so matrix times vector, now we have a vector. Okay, so and what was it? It was an m by n matrix times an n by 1, so we have an m vector. M is going, okay, m is the number of components we have. We want to know what is the ith row of this. Well, what is that going to be? It's going to be the ith row of this dotted with this vector. Okay, so we're going to have the gradient of fi dotted with x minus x naught. Right? This is how our usual matrix vector multiplication works. If we want the ith component of the result, it's row I dotted with this vector. Okay? Row I we said was all of the different partial derivatives of fi, so that was precisely the gradient of fi. All right, and then we stare at that for a second, and we realize, well, what is this? This is a dot product. So this is a dot product from 1 to n of, okay, the components of this are partial derivatives, the partial derivatives of fi, dotted with the jth component of this. And what do we have here? What we have here is exactly what we get when we ask fi to be differentiable. It's exactly the same object. So if I want to write this whole thing as a vector, well, the ith component of this is fi, the ith component of this is fi of x naught. And now the ith component, we can also write as a component of vector, it's the ith component of this vector. And this gives us a more compact way, or an alternate way, of defining differentiability. Okay, we're going to say that f, which goes from Rn to Rm, is differentiable if the limit as x goes to x naught. Okay, and now I'm going to just write the limit of a vector. Okay, so I'm going to have f of x, and we know that it has all these different components, f1, f2, up to fm. So f of x minus f of x naught minus. And now we realize that this is precisely the ith component of this matrix vector product. So Jacobian of f times x minus x naught, all divided by the length of x minus x naught, should be the zero vector. Are we happy with the definition of differentiability? I haven't changed the definition of differentiability, but what I've done is introduce notation so that we can write this in a compact form instead of having to list out all of these different components separately. And then in particular, this somehow recovers the same idea that we said a differentiable function should somehow be well approximated by its linearization. Well, now we have a differentiable function that's vector valued, so its linearization, instead of just having a derivative we have to worry about or a gradient we have to worry about, now we have this Jacobian that we have to worry about that's going to tell us what our linearization looks like. So we still somehow expect that f of x is somehow approximately equal to, okay? So here's our constant, and then here is our linear term. Right, where this Jacobian is evaluated at x naught. So this is a constant matrix. Okay, so this is really constant plus, okay, constant. So here's a linear term. And something like this, f of x on the left-hand side is whatever it is. It could be very nonlinear. But what's on the right-hand side, we're going to call an affine transformation. That is, it has a linear part and a constant part. So we're going to say that a mapping of the form t of x equals u plus a x minus x naught. Okay, where u is a vector, x naught is a vector, okay, and they're both constants. Okay, and then this matrix A is a matrix. Is called an affine mapping. Okay, and anytime we have a differentiable function, we should be able to find an affine mapping that well approximates it. Right, that approximates it in the sense that f of x minus t of x divided by x minus x naught is equal to 0. Okay, so for example, we could be asked to find an affine mapping T such that the limit as x goes to x naught of f of x minus t of x over x minus x naught is 0, and we could be given some specific information. So let's say that f is x squared plus y squared, x sine y, and e to the xy, and x naught is going to be 1, 0. Okay, so what do I have to do to find this affine mapping?
Calculate the Jacobian?
I just have to calculate a Jacobian, right? So although the problem statement talks about a limit, we don't have to do any crazy calculations with limits like the last example that we did, forcing these things to be 0. We know from the definition of differentiability what this affine mapping has to be. All right? This is a nice function. All its components are nice differentiable functions. We have theorems to that effect, so we don't have to go back to first principles on all of these. And that means that we know that the affine mapping we want is going to be precisely this one. We just need to plug x naught into our function, and then we need to compute its Jacobian and plug x naught into the Jacobian, and then we've got our affine mapping. Okay, so here what would I do? I'd say, well, f of x naught I need. Okay, so that I plug in 1 and 0, so I get 1. 1 times 0 is 0. All right, e to the 0 is 1. Okay, and then I need a Jacobian. Okay, so my first row will be the gradient of this function, 2x, 2y. The gradient of this function, sine y, x cosine of y. And the gradient of this function, so y e to the xy and x e to the xy. Okay, and now we don't need to keep all of these nonlinear functions in here. We only care about this, again, at this particular point, x naught. So we plug x naught in. Okay, and what do we get? We get 2, 0. Sine of 0 is 0. Then we have 1 times 1 is 1. Y is 0. X is 1. So we get just this constant matrix that we have to worry about. Right, and now we have all the information, all the pieces that we need in order to build our affine mapping. Okay, so we say we know that T of x is just going to look like our usual linearization. So we're going to have f of x naught plus this Jacobian times x minus x naught. And now we know what these pieces are. So we have a 1, 0, 1 plus this matrix times x minus 1 and y minus 0. Okay, and we could simplify this if we want to. We get 1 plus 2x minus 2 when we multiply that out. Okay, so that's 2x minus 1. Here we get 0 plus y. Here we get 1 plus y. Okay, and now we know that close to this x naught, this function should track pretty well with this linear function. Okay, are we happy with affine mappings? Right, so again, it's no mystery how to do these limits. When you see problems like this, don't panic that this is a big abstract problem or something where you have to do a crazy limit with lots of details. It's really just a plug in the formula, yeah.
So why the limit was given? Just to know what the function is differentiable.
Why is the limit given? So this is really just the definition of differentiability, right? So the definition of differentiability really just means that such an affine mapping exists that makes this limit equal to 0. So there's different ways of asking the same question. You could say, what is the affine mapping that best approximates this function? But you have to clarify what you mean by best. So this is what I mean by best, that when I take the difference and divide through by x minus x naught, it goes to 0. And then that is a uniquely defined affine mapping.
Is there kind of like a geometric intuition behind affine mappings?
So what do we have? We have, the components are maybe easier to picture because they're real valued functions. They're well approximated by their tangent planes. This is really just saying all of these mappings are well approximated by a tangent plane locally.
Gotcha.
Then we have some of our usual theorems. Differentiable functions are continuous. Okay, we don't have to reprove this. Because we already proved it for scalar valued functions. And now differentiability just said, well, each component of this is differentiable. That means each component of this is continuous. And if all the components are continuous, then trivially the whole thing is going to be continuous. Okay, so there's nothing new to prove here. A lot of our results hold. The other one that holds just trivially, suppose that all components of the Jacobian exist and are continuous. Okay, in some neighborhood of x naught. All components of the Jacobian of f, then that gives us that f is differentiable. Okay? And again, that's not something we need to reprove. It works because we can take this component by component. We get a chain rule right away. Okay, so if we want to take compositions of these vector valued functions, we have a simple way to do it. So let's suppose we have f goes from Rn to Rm. Is differentiable at y naught. Okay, we have, that's our outer function. We have another function, which goes from, let's say, Rk to Rn. And it's differentiable at some x naught. And of course, these y naught and x naught are related to each other through this function, like we've had for our normal chain rule. So with y naught equals g of x naught, okay, then this composite function. So if we take f of g, so what does f of g do? It takes something in Rk, okay, which becomes Rn. Then our variable in Rn gets plugged into here and becomes Rm. Okay, this is differentiable at x naught. And we have an expression for the Jacobian. Okay, so it's our usual expression, Jacobian now, of our outer function. Okay, times the Jacobian of our inner function. So now this is a matrix product. Oh, so we know, last week I think we did a chain rule for scalar valued functions, and it was a bit of work proving the chain rule. And now we've just turned this into an even bigger problem where we've got matrix products. But we don't have to be daunted, because even though there's more going on in here, more to keep track of, we can use the chain rule that we proved last time, right? Because everything that we said about differentiability is really just a component by component thing. Okay, so you don't have to be scared when you see this. You could realize we're going to prove this very quickly. Okay, so yeah.
Is the chain rule in applied math time consuming?
Is the chain rule in applied math time consuming?
Computationally.
Well, it depends on your F and G, I guess. I wouldn't say that. I don't remember ever spending a significant portion of my life doing the chain rule. No, so I'll be honest. If I have to differentiate a function or integrate a function, I open up Wolfram Alpha or Mathematica or something. Right? I don't spend a lot of my day doing these computations by hand.
It's not apply this in simulations, or
So you can certainly apply this in simulations, yeah, and let a computer do the time-consuming parts of it, ideally.
Yeah, but for the computer, is
it a big time-consuming issue? It depends. It's going to depend how big these matrices are at the end of the day. So I guess the answer is maybe. Matrix vector products can be a big deal depending how big your matrices are. So yeah, the short answer is yes. If this has a million components and this has a million components, or if it's in a million by million matrix, say, right, then it's time-consuming to do these multiplication, and you may want to look for extra structure in your problem that lets you take a shortcut or approximate this in some way. Yeah, I mean, these are questions you have to ask if you're a computational mathematician. Yeah. Even though you say, yeah, I have a nice formula and algorithm and I've proved it converged, it doesn't mean it's practical. Okay, so the first part of this conclusion was that this beast is differentiable. There's nothing to prove there. We've already done it because, well, if we just take it a component at a time, the first component of this is f1 of g of x. F1 is a scalar valued function that goes straight into the chain rule that we proved last time, and we know that, therefore, the first component of this is differentiable. Same with the second component and all the other components, okay? So each is certainly differentiable. Okay, since H1 all the way down to M. So that was last week's integral. Okay, and last week's chain rule also gave us the formula for the partial derivatives of H1, for the partial derivatives of H2, and so on. So now we just need to try to show that those partial derivatives do indeed match with this formula for the Jacobian. Okay, so let's go through what we're going to do. This is a matrix. It has a whole bunch of components. So we need to go check each component and check that the ijth component of this matches the ijth component of this matrix-matrix product. Okay, so this is the partial of hi with respect to xj. Okay, where, just recall off to the side here, hi of x is fi of g of x. And this is scalar valued, which means everything we know about scalar valued functions is fair game. Okay, so let's do our chain rule on this. We have a chain rule for this function, so we can use it. We know that we have to run through all of the different partial derivatives of fi, and then multiply them by the appropriate partial derivatives of g, of the different components of g. Okay, so let's run through all of these different components. Just check, yep, f has n inputs, so there's n possible partial derivatives. Okay, so this with respect to the mth component. Sorry, it's really distracting when you're whispering and talking back there. Okay, this evaluated at g of x naught. Okay, times the appropriate partial derivative of g. Okay, so the mth component of g with respect to xj. Okay, and now let's see if we can try to identify that object as the ijth component of this object. Okay, so what is? We're fixed at fi. We're running through all the different partial derivatives. Okay, so fixed at fi means we're going through the ith row. We're taking the gradient of fi. Okay, so what is this? This is the gradient of fi. In other words, it's the ith row of the Jacobian. Okay, and then what are we doing here? Well, all of these are with respect to xj. Okay, so we're in a fixed column, the jth column, and now we're just going through all the different components of g in the jth column. So this is the jth column of the Jacobian of g. All right, so ith row of one matrix, dotted with, right? This is a dot product, right? Because we're going through component-wise. So we've got the ith row of this matrix dotted with the jth column of this matrix. And that, if you remember your very basics of the matrix algebra, is indeed the ijth component of this matrix vector product. So this we can identify as indeed exactly this, evaluated at x naught, and then we take the ij component. Right, and again, I didn't have to do any magic to get to this result. You know, when I wrote out the theorem, I wrote this out ahead of time, but I wouldn't particularly have had to know this ahead of time, right? It kind of pops out naturally when we just say, let's work out what is the, you know, this Jacobian is some matrix, so let's work out its components one at a time. And with very minimal work, we were able to identify this as a matrix product. So there's no magic here. We did all the work last week. Right, so if we want to take a concrete example, okay, with so f of y is going to be y1 squared plus y2 squared plus y3 squared, y1, y2, y3. And g of x is going to be x1, x2, x2, x3, x1, x3. Okay, and then maybe we could be asked to find the Jacobian of h at some x naught, where let's say that x naught is equal to 1, 2, 3. Okay, so we know what pieces we have to compute. We have to compute g of x naught. We have to compute the Jacobian of these two different functions and plug in our reference point to it. Okay, and again, that's it. There's no magic. Okay, so g of x naught is going to be, all right, 1 times 2, 2 times 3, 1 times 3. All right, we need the Jacobian of f. Okay, so f has two components, and then we're going to get 2y1, 2y2, 2y3, and y2, y3, y1, y3, y1, y2. Okay, and where do we care about this? Well, the only place we care about this is at this particular point, g of x naught. So we just need to plug 2, 6, 3 into there. Okay, so 2, 6, 3. All right, 6 times 3 is 18. 2 times 3 is 6. 2 times 6 is 12. Right, and then we similarly need to compute the Jacobian of our function g. G has 3 components. Okay, so partial derivative is going to be x2, x1, 0, 0, x3, x2, and x3, 0, x1. And again, we only care about this at a particular point. Our reference point now is going to be 1, 2, 3. So at x naught, we get 2, 1, 0, 0, 3, 2, 301. Right, and those are all the building blocks we need in order to compute the Jacobian of H to do our chain rule. So now our Jacobian of H at our reference point x naught becomes, well, the Jacobian of F, that was this matrix, 4, 12, 6, 18, 6, 12, times Jacobian of G, 2, 1, 0, 0, 3, 2, 3, 0, 1. Okay, 2 by 3 times 3 by 3, the sizes work out, that's good. Okay, and then if I've done this multiplication right, I should get 26, 40, 30, 72, 36, 24. Right, questions on the chain rule? It's not bad, right? We did all the heavy lifting last week, and now this week we get to kind of reap the consequences of it, reap the benefits of it. Okay, so that's our chain rule. The other thing we might need to do with matrices, now that we've brought matrices into the picture, sometimes we want to have a concept of the size of a matrix. We've had to do this for vectors. We've taken the length of a vector. Now we want to use that to also build up, in some sense, the length or the size of a matrix, which there's different ways of defining this. But here's one that will be useful when we're trying to do the kinds of bounds we want to do. So let's introduce the norm of a matrix. So this is what I want to be able to do. I want this. If I have some object like A times X, so A is a matrix and X is a vector, so this is a vector, I can take the length of this. What I would like to be able to do, I would like to be able to sort of bound this in the way that feels like I would normally bound things. You know, usually if I multiply a bunch of things together, take the absolute value, I say that's bounded by the absolute value of the components. I want to be able to do that here. So I want my norm of A to somehow have this property, that this product is bounded by the norm of A times the length of my vector X. And I want this to always be true. So what I'm going to do is simply define the norm of the matrix A to be the smallest. So this is a real number, right? We took our matrix and turned it into a real number somehow. I'm just going to define this to be the smallest real number that makes this true. Okay, so this is how I'm going to define the norm of A. The norm of A is going to be the smallest possible real number okay, so such that the length of A times X is always less than or equal to C times the length of X for all X. Okay, and that's the norm of my matrix. And I mean, there's different ways you can define different norms. You know, this here, I've taken the length that we've been working with, basically the Euclidean vector norm, but there's different vector norms, the L infinity norm, the L1 norm, and different vector norms will create different matrix norms. So right now, I'm assuming we're using Euclidean norm, and this is the norm that we're going to get. Differentiable mappings there's other kinds of bounds that we can put on them. So we get Lipschitz bounds. For differentiable mappings. And actually, there's two directions that we can do this. So I'm not going to prove all of them. They're kind of just technical proofs that are not that exciting. But let's suppose that we have this transformation, and it's continuously differentiable. Okay, on some neighborhood of x naught. Okay, then, okay, so what are we trying to do with a Lipschitz bound? We're trying to bound f of x minus f of y by some constant times the length of x minus y. That's how we define a Lipschitz constant for a normal scalar valued function. So what this is going to tell us, okay, I'm going to write these out really precisely because it's going to become important to us in about a week. So pick any tolerance you like. We can find a delta, okay, such that the length of f of x minus f of y, okay, is always less than okay, now these are, okay, x and y are close to x naught. So we'd like to say, if we're thinking about linearizations and things, that this is pretty close to the Jacobian of f times x minus y. Right, that has the flavor of our usual mean value theorem, all these things. It's not going to be exactly evaluated at x naught though, so what we're going to do is say this. Is this pretty close to the norm of f of x naught, but plus some little epsilon times the length of x minus y. Okay, and this should be true whenever x and y belong to this delta neighborhood about x naught. Okay, and this is when you're doing this at a point. Now, if you think instead about doing it on a set, a compact set, then you could come up with a concrete number that works everywhere on that set. Just like in lower dimensional problems, we'd be able to say, well, f of x minus f of y is going to be bounded by, well, the biggest value of the derivative times x minus y. That's really all we're doing here. We're just making the higher dimensional version of it. I'm not going to write out the proof of this. You can look it up if you want. It's technical and not that exciting. And then the other direction, if things behave themselves, you can also go the other direction and you can come up with a bound from this side. That could be useful for a lot of things. For example, you know, we're used to when we're doing limits and continuity problems, trying to bound things from above. See, it's no bigger than this. But it could be really useful to go the other way and say, I want to solve, say, f of x equals 0. Well, let's say I do some numerical simulation, and I find some x tilde such that f of x tilde is equal to some small number. So then the question I have is, well, it seems like I've gotten really close here. And the question I have is, given that my f value is very close to 0, does that mean my x tilde is actually really close to the solution? So my question is x minus x tilde small? And if it is, how small? Can I quantify it? So that's why I would like to have something that says, well, actually the length of x minus y is less than some constant times f of x minus f of y, because then I could say, yeah, actually my error is small, right? If this is epsilon, then my error is less than some constant times epsilon. Well, that may not always be the case. I mean, if I imagine a function like this, where it has a very, very flat gradient for a while, you know, it may be that the real solution I want is over here. The x star I found is over here, not particularly close, but I've come up with a very small epsilon over here. So f is small, but there's somehow going to be a very large constant that pops up here. And these are the kinds of issues we want to worry about if we're solving things numerically, say. Because I can't tell exactly what my error is at the end of the day. I never know that. If I knew how to calculate my error exactly, I wouldn't need to do numerics. All right, so all I can usually say is, well, I came up with something and it gave me a small result. Is that any good? And then you need to know, am I in this situation or am I not in this situation? And you know, you can see from this picture, the problem is that the derivative is very close to 0 here. And we're going to have a similar issue here. If the Jacobian is somehow very close to singular, then it's not so good. So the other direction of this is let's let f, okay, be our transformation. All right, it's square this time. Square should make sense, the same number of inputs as outputs, because now somehow in my head I'm trying to solve a system, right? So I should probably have the same number of equations as unknowns going on here. Okay, so I have my square transformation, and it is continuously differentiable. Okay, on an open set. Okay, that contains some compact set D. Okay, so in other words, I have some compact domain that I'm working in. I want to do things in this compact domain, and I can somehow this domain maybe takes up space. So I'm not in 2D, but somehow my domain is only one-dimensional. And that's where this bit about an open set. So I have this thing, my function is continuously differentiable on some set that actually takes up volume in my space. And then I look inside there on some compact set, because anytime we want to like maximize things, we need to be on compact sets. Okay, so we have some well-defined thing. Okay, and then okay, then let's see. There exists some m belonging to R. Let's see. I'm going to give you the last two lemmas here. So some m belonging to R such that there is f of x minus f of y is less than m times x minus y for all x, y on my compact set. And then part 2. Okay, so that says I can take the first direction of my result away from x naught onto a set. And the second direction is I want my bound from the other side. Okay, so it is continuously differentiable. Okay, on a neighborhood, so again, a set that contains space, takes up space. On an open set containing x naught. And we don't want to run into the situation where we have a zero derivative, so to speak, where our Jacobian is singular. Okay, so we have also an invertible Jacobian. Okay, then, no matter how small your tolerance is, we can find a delta such that, and now we mimic this result from the other direction. Okay, such that f of x minus f of y is bigger than or equal to, okay, 1 over the norm of the inverse of the Jacobian minus epsilon times x minus y. Okay, so what happens here? If the Jacobian is nice, maybe the norm of the Jacobian is close to 1, then that's going to tell me that my bound f of x minus f of y is going to be kind of proportional to x minus y itself. Okay? So in other words, if this epsilon is small, then my error is going to be small. But if this is pretty close to singular, right? So in some sense, the Jacobian is close to 0, then all of a sudden, I'm not going to get any useful information out of this, right?
So it's kind of like blow up, I guess?
It's, right, exactly. So we're going to get blow up, and we're going to get, this is going to get very close to 0 here. And all of a sudden, we have x minus y is bounded by, well, this divided by something close to 0. All of a sudden, that's a big number, right? And even if this is tiny, x minus y could be very large. Okay, so we have these two directions. I've written these lemmas with all the technical details, which is going to turn out that we're going to need these in the next couple classes, because from here, we've got the building blocks of continuity, differentiability, all of these things. Now we're going to come back to our question of, but now I have a big system, and I actually want to know if I can solve it. Okay, maybe I've discretized my PDE, and I have a million variables and a million equations. Does it have a solution? So these are the kind of questions we're going to start exploring over the next couple of classes. And then it's going to matter that we have all these technical details exactly right.